in this I think we have already completed the entire color science and color management module, but I thought of adding a special lecture to this series related to colorimetry and the creation of the first numerically or quantifiable method to define a color, those processes. So as I have already told you in the class that it all started in the 1920s when two scientists, Wright and Guild, conducted a series of color matching experiments with 10 and 7 respectively standard observers. So what was the aim of the experiment? The aim of the experiment was to get a better understanding of colors and methods to quantify them, methods to measure them, and so with this intent I think the experiment was done at that time, and ultimately 1931 during the meeting of the CIE, they accepted the findings from the experiments, and that led to the creation of the first so-called quantifiable color space as such. So let me just give you a very brief overview of what the color matching experiment was. So here as you can see that this person over here, this person is the standard observer. Okay, so as you know that the LMS responses vary from one person to the other. Now in order to get a uniform visual color perception that represents a uniform perception for the entire human population, we need multiple observers, we need multiple standard observers to be matching colors in this manner, so that we can get a statistically significant result with very low deviations. So this person is the standard observer. This person have been tasked with matching the color that has been matching this particular color which is present in the fixed field. As you can see, this particular color is this is the white screen on which this light is being made incident on. This is controlled by the person who is conducting the experiment, and this part, that is the adjustment field, this is basically conducted by is controlled by this standard observer. So what they have used, so technically speaking, that any light, any visible light of a particular color can be matched with by mixing some quantity or some proportion of red, blue and green lights, because as you know that these are known as the additive primaries. So theoretically speaking, all these, any color within the visual spectrum being roughly from 400 to 700 nanometers, can be matched by some combination of all these additive primaries, right? So this is what exactly the intent or how the color matching was actually done. So the standard observer has control over how much amount of light has to be mixed, which light, the red, blue and green lights that has been used here. So the wavelength that were chosen for conducting this experiment, that roughly simulates the LMS responses of our eyes. As you know that L responds to the red region, M responds to the green region, and S responds to the blue region of the visual spectrum. So what they thought of was they used specific wavelengths of red, green and blue lights to simulate the LMS responses of the human eye. So for red light they chose 700 nanometers of wavelength. For green light they chose 546.1 nanometer of green light, and for blue light they chose 435.8 nanometer of blue light. So the procedure in which the experiment was conducted was that the standard observer was actually asked to match this light which was made incident on the white screen in the fixed field using or adding various proportions of red, green and blue additive lights. So after this experiment was done, it was observed that some relative, if the quantities of light, if the relative quantities of light or intensities of light were mapped to to their relative wavelength in nanometer of the light, this being the intensity of light or the relative proportion of the light that were additive lights that were used for matching this particular color in the fixed field, versus along with the wavelength in nanometers of those particular lights that were used for matching those particular colors in the fixed field. So in order to map, after conducting the experiment, these data were mapped, and ultimately what was obtained is some types of plots like this. So this, on the x-axis we have the relative quantities of the red, blue and green light that were used for matching all the lights that were given by the experimenters in the fixed field, versus the wavelength, relative wavelength of the light that were used for by those particular lights. So as you can see, this blue line represents the relative quantity of blue light that were required in order to match, and what wavelength, relative quantity of blue light of a certain wavelength range, in order to match all the colors that were given during the experiment. Similarly, this amount of green light of this particular wavelength range were used to match all the colors that were given during the experiment. Similarly, this amount of red light were used of this particular wavelength range in order to match all the colors that were given during the experiment. But interestingly enough, you see that the red has got this negative lobe, right? So when we are talking about adding colors in this experiment, as you can see very clearly, that we are talking about mixing and adding colors, adding additive colors in order to match some other color, right? Now in that scenario, where does this red light comes from? It actually stems from the idea that for certain colors, now which colors, that we will come to know at a later stage, in order to match certain, okay, I think you guys can also get a fair bit of idea on which colors do you think are represented during this wavelength, that is between 450 to 550 nanometers. What is the nature of the color? Which color am I talking about? So that is something I'll be telling the answer to this question. But between 450 nanometer to 550 nanometer range, wavelength range, what is the nature of the color that were considered in this region? So as I was saying, that in certain colors, for certain colors in the range of 450 to 550 nanometers, the red light was added to the fixed field itself. It was removed from the adjustment field. That means it was removed from the standard observer side, and red light was added to the fixed field itself, so that the standard observer could match the color that is in the fixed field using green and blue light. Now the question is, why did this occur? I mean, what was the necessity to to remove the red light from the adjustment field and add it into the fixed field? The reason behind it is that obviously it's common sense. I mean, definitely there were colors which could not be matched using red, green and blue light. So as a method to trick the system, the red light was brought from the adjustment field and added to the fixed field, so that the standard observer could match the light which was portrayed in the fixed field using green and blue light that was present in the adjustment field. So this is how it was done. Now obviously, as you can see that red light has got negative lobes. It's difficult to design imaging systems having more than 3-4 channels. It's a computationally costly as well as it's complicated to design. So if in this case for this type of an imaging system, having R value 1, R value both positive negative, green value positive negative and blue value also maybe R, you can see that R value is both positive negative, green and blue are only positive, but as soon as you go on increasing the number of channels that are required in order to create an imaging system, it becomes extremely difficult, and it becomes computationally very costly to design such systems. So in other words, it's difficult to work with negative values, right? And it doesn't have any meaning. What can negative red mean? Just that the red light was removed from the adjustment field, and how much amount was removed, exactly that amount was added to the fixed field. In order to explain this this phenomenon, the red went into the negative side of the plot. As I told you that this is quite difficult to design, what the scientists at the time did, they applied a very neat trick. They instead converted all these curves that were obtained. Okay, so I didn't mention this. So these curves, these blue, green and red curves, these came to be known as the CIE RGB color matching function. Why color matching function? Because every point on this curve can be, so if I am asking you, tell me what colors, what amounts of light, not colors, what amount of light will be required to reproduce a light having wavelength of, let us say, 640 nanometers. So you will say, okay, so this is 0% blue, this is maybe 0.05% green, and so you convert, not percentage, so you convert the scale. So 0.05 quantity of green, 0 quantity of blue, and let us say 0.3 quantity of or amount of red. So using these curves you can ultimately obtain the relative quantity of red, blue and green primary lights that is required to reproduce any color that you see in the visual spectrum between 400 to 700 nanometer. So this is how it is basically, this plot signifies that how much amount of light, relative quantities of light, primary lights, that are required to reproduce any light that we see along the visual spectrum. So now coming back to the point that I was just referring to, that is, since it's difficult to work with negative values, what the scientists did, they converted the entire plot into positive values. This was done using a mathematical operation which is known as linear transformation. So people who are into linear algebra and all of that stuff, they know already what a linear transformation is. And so after conversion of those particular curves, that is the CIE RGB color matching functions, into all positive values, you get these curves, right? So something like, one curve is this is the red which went into the negative, now it has come back to the positive, the green and blue were already positive. Now you see, how was it obtained? It was obtained by applying some mathematical function onto the CIE RGB color matching function, this one, right? So when you are talking about the CIE RGB color matching function, these are all real lights and real colors. The human eye can perceive this. But as soon as you do some linear algebra or linear transformation and mathematically operate on these particular numbers, do you think those numbers are real numbers? I mean, not in terms of real and imaginary numbers, but do you think that these, I mean, what I'm trying to say exactly is, you can perceive this type of colors, you can perceive these lights with the human eye. But I am saying, after converting this into some other coordinate space, you get something of this sort. These type of color matching functions, they represent the CIE RGB color matching functions, but their nature has changed. This is a mathematical operation. This has been obtained as a mathematical operation on the CIE RGB color matching function. These are not real in nature. By real, I mean the human eye are not able to perceive these colors. These are imaginary numbers that have been, imaginary numbers, remember, I am not talking about root over -1, not those imaginary. I am talking about because some mathematical operation was conducted on the CIE RGB color matching function, you get some other sort of numbers that you plot in this type of coordinate system to get this type of colors. Now these are all imaginary in nature, they do not exist in real life. These are only numbers, mathematical numbers. That is all I am going to say. So these curves where all the color matching functions are on the positive side, these came to be known as the CIE XYZ color matching functions, and they are represented by a three primaries. These primaries are known as the CIE tristimulus value or CIE imaginary primaries. That is known as, that is denoted by capital X, capital Y and capital Z. Okay, so যেরকম করে as we used the three RGB primaries to plot these curves, that is the CIE RGB color matching functions, and after mathematical conversion we, in order to convert all this data into positive side, we are getting this CIE XYZ color matching function. They also are represented by three such primaries, but the difference between these three primaries and your RGB primaries is that these three primaries are imaginary in nature, they don't exist in real life. That is why these three primaries are known as imaginary primaries. They are also a manifestation, these three primaries, imaginary primaries, are also a manifestation of these your RGB primaries, right? These are manifestations of RGB primaries, these XYZ primaries or imaginary primaries. That is why they are known as tristimulus values. Why tristimulus? Because they represent three sensations of the human eye, that is L, M and S type of cone sensations of the human eye. Okay. Now from the the color matching function, let me just give you a very brief idea of how we can correlate this concept of color matching function in color space. So in the previous lectures we will be talking about the CIE XYZ color space and small xy color space and all of that. So let us take a look at how it is done. So consider this 3D coordinate system. Okay, so this 3D coordinate system is basically your RGB color space. You know, RGB color space is cubic in nature. So this is the R red axis, this is the green axis, this is the blue axis. See, I am repeating this entire experiment. First I told you, I explained this particular color. This is known as the 1931 color matching experiment by Wright and Gill. Now I first explained this or correlated this color matching experiment in order to get these type of color matching functions. I am explaining this color matching function again, but now in terms of color spaces. Okay, first I explained the color matching experiment in terms of color matching function. Now I am explaining the same experiment in terms of the color spaces. Okay, so this is a RGB color space, right? So this point may be represented by maximum value is 100, this point may be 010, and this point may be 001, right? So what do you think is the maximum value in this coordinate space? The maximum value is 111. See, so how to represent that? You draw a vector. So in 3D space, এটা তো 2D space, মানে এটা বোঝানোটা যাচ্ছে না, কিন্তু ইমাজিন এটা একটা 3D space, একটা ঘর নিয়ে চিন্তা করো। এবার ইমাজিন a point in the space which is touching the opposite end of the diagonal in this cube whose value is 111. তাহলে এটা কোন পয়েন্ট রিপ্রেজেন্ট করছে? This is the white. That means R, G and V, everything is maximum, hence it is by mixing maximum quantity of equal energy R, G and V, we get white. So that is white. Okay. Now similarly, any point we can obtain any point in this particular. So let me just erase this because we won't be needing this particular thing actually. So what we can do is we can obtain any point. We can obtain any point in this 3D space which will be some combination of R, G and V. So we can draw vectors starting from this is the origin, this is the 000 origin. So we can draw any vector in this 3D space that would represent some combination of red, green and blue. In this experiment we matched a color given in the fixed field by changing the relative quantities of red, green and blue lights in the adjustment field. So that means relative quantities of red, blue and green will be represented here by means of a vector, right? So you draw any point from the origin. So all these points will be representing some relative proportion of red, blue and green light, right? So that is what I am saying. Now do one thing. Draw or join the points of these vertices. Okay, so what do you get by joining the point? You get a plane, a triangle, equilateral triangular, that is not a 3D, that is in 3D space, but this is a plane. This plane that we obtain by joining the three vertices of this color space is known as the unit plane. Why? The maximum values that are obtained here is 1, 1, 1, that is the unit plane. Now, in order to map all the colors that were obtained by the standard observer by mixing different quantities of red, blue and green primary in order to match the light given in the fixed field, that may be drawn from the origin onto the unit plane. তার মানে প্রত্যেকটা ভিজুয়াল স্পেকট্রাম, মানে আমরা তো এই যে ট্রায়াঙ্গেলটা আছে, দিস ট্রায়াঙ্গেল রিপ্রেজেন্টস দ্য এন্টায়ার গ্যামাট অফ কালার that is theoretically possible or within the visible spectrum. Why? This particular triangle encloses the gamut of colors that is created by some combination or the maximum combination of R, G and blue light, right? That means all these colors that the standard observer will be observing by changing the relative quantities of red, blue and green light can be obtained by drawing vectors from the origin onto this plane. Like this, we'll get a series of points like this. Right? Are you understanding the point or not? I am saying that this particular triangle is representing all the colors that are theoretically possible within the visual spectrum. Why? Because this is a plane that is enclosed, that encloses the area of maximum values that are obtained from red, green and blue colors. So this particular triangle will enclose all the colors within them, and in this color matching experiment you can see the standard observer is matching some colors as is required in the fixed field. So if I plot all those points, all these particular points are some combination of red, blue and green, some combination of red, blue and green that is observed by the standard observer, and I am plotting all these points on this unit plane, right? So next thing that I will do is I will join all these points, right? This particular locus that I got is basically known as the spectral locus. This spectral locus represents all the visible colors, all the colors that are visible to the human eye within the visible spectrum. Okay, I am repeating. By joining all the points that the standard observer saw in this unit plane, RGB unit plane, this is known as the spectral locus. Why? This will contain all the colors that are visible to the human eye, right? Now after doing this, so this is basically, as you can understand, this is in the, you see in the what is it specifically in the 3D space, right? Now working in the 3D space might get difficult time to time, so what we did was, what was done in that particular period was, it was converted into a 2D space. Okay, from this 3D space the spectral locus was projected into a 2D coordinate space. Due to this, what was obtained is basically known as the, I think I have the picture, wait, I think I have the picture here somewhere. This is particularly known as the CIE XY diagram. RGB unit plane. This is the RGB unit plane in the RGB color space. After all the points in the that were obtained after the color matching experiment by the standard observer, all these points were joined together to form the spectral locus. Now, as I already mentioned, that that working with 3D spaces may get difficult from time to time. So that is why at the time what was decided was this spectral locus was converted in a 2D space. Now you can see the shape of this particular spectral locus. It is looking like a tongue. So after conversion, this particular spectral locus started to look like this. Now as you can see over here, this space, this diagram came to be known as the CIE chromaticity diagram, and this coordinate system came to be known as the CIE chromaticity coordinate system. This is represented by two axes. One is the small x, another is the small y. Small x is obtained. Small x is basically a manifestation of your tri-stimulus value z. Small y similarly is y divided by x plus z, whereas z is equal to 1 minus x minus y. Right? Now, small x is basically nothing but a manifestation of your tri-stimulus value only. The only thing that was done is, jehetu the spectral locus now was in a 3D space, it was difficult for working with a 3D space. Now it was converted into a 2D space. This space is known as the CIE small xy chromaticity coordinate system, and this particular curve is known as the CIE chromaticity diagram of the CIE spectral locus, CIE xy spectral locus. Here one information is missing. As you can see, you are getting the hue along all the points of this curve, right? From 400 to 700, all these points you are getting areas of pure hue. As you move from any point to the center, the saturation is decreasing. So you are getting hue information and saturation information, right? But what you are missing is the lightness information. Lightness information is given by the capital Y. Luminance information is basically given by the capital Y. So together, if we consider the small x, small y and capital Y, we get XYY or YXY, however you write it. This is the color space together, because only XY color space we cannot use because we do not have the lightness information at that particular point. Now also you can see that in this particular curve, there is at the center of this particular curve is what is known as the ideal 0.33, somewhere over here, 0.33, somewhere over here. This is the known as the ideal white point. What is white point? The white point is the area or the region of least saturation, where there is no saturation of any color available. That is what white point is. So as you move from any point on the spectral locus, on the border of the spectral locus, into the inside of the spectral locus and reach up to the white point, you will see the saturation gradually is decreasing, right? So I will talk about a various, also remember I talked about how in the CIE RGB color matching functions the red was going into negative side. So just I will try to explain in a different way also. So let me just try to draw the CIE chromaticity diagram. So something like this. So here is 400 nanometer, this is 700 nanometer, so it is going like this. Okay, so we talked about what type of primaries did we use during the color matching function. For red we used 700 nanometer, for green we used I think 546.1 nanometer, and for blue we used 435.8 nanometer, right? These were the ideal the RGB primaries that were chosen. Now let us, 700 is this one, so this will be the red color. 435, let me see, where is 435, somewhere over here, 435. So somewhere over here is 435, this will be the blue color, and green 546. Let me see, 546 is over here, right? So here is 546. So just join these points. This will be nothing but the, tell me what is this? This is nothing but the RGB unit plane, which I already showed you over here. In the RGB 3D color space, I told you the gamut of colors that is theoretically possible to be which is a combination, some combination of red, green and blue, and we join these points vertices together to get a unit RGB unit plane. This contains all the colors that is possible using some combination of R, G and B, and within that is located the spectral locus. So this will be that RGB plane. But you see here, this region, that means this is the green region. Now you consider any point in the green region, right? And this is the red region, this is the red region. you add red to, so green, this particular green is not achievable, right? Is not achievable by mixing. So because our theoretical limit of all colors that are possible by some combination of red, blue, the red, green and blue is this area. But we see green area, as you can see in this particular diagram, green area, this is falling outside of that RGB unit plane, right? Now what to do? If we add some red, if I am adding red, in which direction will this color move? This direction. Red is in this direction, this point. If we add some red to this green, the green will shift and reach over here. So that means then only this particular green or this particular color will be achieved by matching or adding some combination of red, green and blue. Again I am repeating myself. So you see, this is the RGB unit plane that we talked about, but we see green is lying outside this RGB plane. So that means what? This is not possible by mixing some combination of RGB plane. How is it possible? Because it is lying outside the RGB unit plane. Now one way to adjust this, or one way to reproduce this particular color, if we add red to this green, only then the color will shift in this direction, in this particular direction, and if the color shifts from this point to this point, this color will be achieved. As long as it is within this RGB unit plane, then it will, this or RGB gamut, then this particular color will be achieved. So I have explained the reason why red goes into the negative. So that means what? You have to remove red from the adjustment field and add red to the fixed field in order to reproduce certain colors from how much? 550 to, I think 450 to 550 nanometers over here. 450 to 550 nanometers, which is essentially the green region of the XY coordinate space, right? So that is how you can explain why red is going into the negative low, because green is falling outside of the RGB gamut, and by adding red to it, we can bring or we can create this color by adding some quantity of RG and E light. Okay. Now also another thing, so if I have already told that this point is the ideal white point, right? Now when this is the area of pure hue. Now when you join a line from the area of pure hue to this white point, and you continue the line on the other side, the color that you get on the other side will be the complementary color to the point to the color that is present in this direction. So if we are calling this A and we are calling this B, and this is the white point. So if we join A to the white point and continue the line to the other side of the, such that it meets with the other side of the spectral locus, then this A and B will be complementary to each other. Okay. Also, let us say we have, so as I told you, all colors or all points lying along the spectral locus, this perimeter of the spectral locus is known as the are colors of pure hue, right? And as we move inward towards the white point of the spectral locus, they loses their saturation. So how much? So let us say this point is A of pure hue, and there we have a point, let us call it as C. Okay. Now if I ask you that in respect to A, what is the purity? What is the purity of C? When I say purity can be explained in some terms of how much saturation it has with respect to the pure hue of that particular color, right? So if A is the color of pure hue, C is that same color but of the same hue but with less saturation. So if I ask you what will be the purity of C, so that means what will be the saturation, or what will be the purity of that particular color. So this particular computation is known as excitation purity. It is known as excitation purity. Excitation purity is denoted by PE, P subscript E. So PE is given by x minus xn divided by xd minus xn. So what is xn? Xn yn is the, or similarly for the y coordinate also, y minus yn by yd minus yn. So what is your excitation purity in this case? It will be if the chromaticity coordinate for the white point is xn comma yn, and the area of the pure hue has an excitation purity of xd and yd, and c is what you is the whose excitation purity you want to find, that is x comma y. Then the excitation purity of c is the ratio between the distance between that color and the white point of the illuminant to the distance between the color of pure hue to that of the white point of the illuminant. Okay, again I am repeating, excitation purity is some ratio of that particular color to the white point of the illuminant to that of the distance between the color of pure hue to the white point of the illuminant. So that is equal to x minus xn, x being the x coordinate of the color in question, xn being the x coordinate of the illuminant or white point in question, xd is the xy coordinate of the pure hue in question, and similarly for y. So this is what excitation purity and how to calculate excitation purity is. Okay. So I think this will, I think, do.